Syzygy, episode 25, Picture the Sky. And welcome back to another edition of the Syzygy podcast, episode 25. Today we're going to be talking about astrophotography. Picture the sky. Emily Brunsden joining me on the microphone as ever.
Hello, hello.
What are we talking about today?
Yeah, so astrophotography is one of these wonderful words where you can take a cool thing in normal world and stick astro in front of it.
And it becomes even better.
And it becomes even better.
Yeah. So astrophotography, taking pictures of the sky. Now, I'm going to go out on a limb here and say that I think the large majority of people think that astrophotography, taking pictures of the sky, is astronomy. That's what astronomers do. You look through telescopes and then you see amazing things in the sky, and that's it. That's astronomy. But it's not really,
No,
is it?
it's only the very, very beginning.
I mean, that's where it started,
Yes,
right?
yeah. Well, we just started by just looking up, and then we worked out we could use telescopes to help our eyes to see better. And then we thought, well, we kind of want a way to capture this. And so in the very, very early days of real photography, we started taking photos of the moon. I think it was in about 1840. We took our first photograph, real photograph on plates of the moon.
Yeah, before that it was sort of astro artistry, wasn't
Yes,
it? You're sort
yeah.
of looking through it and then you do a quick sketch.
Yep.
Galileo's got some amazing drawings of the moon and a lot of amazing detail of the structures on the surface of the moon. But they are his drawings through what was probably a bit of a wonky telescope. So it's not quite the same.
Not quite. And so if you want to have that kind of record that's going to be permanent and then you can actually go back to it and keep using it, then you're going to want to start with photography. We started with plates that were they worked a bit like film exposures. And then towards the latter part of last century, we were able to introduce CCDs, which are these fabulous devices. And I have to say, if I'm going to dedicate this show to one particular object, it's got to be the CCD.
Right. Now CCDs are, I mean, it's effectively what everyone has in their cameras now. Isn't
Yes,
it?
yep.
It's turning the light into a digital signal. CCD standing for...
Charge coupled device.
I knew that. I did know that. It was sitting there in the back of my brain. I started that sentence assuming that I was actually able to finish it, and I couldn't. Charge coupled device. Care to go into the physics of that one? Charge
so
coupled?
basically you're turning photons into an electrical signal, and what that's been allowed us to do is basically to improve our signal detection by more than 100 times since using photographic plates. So a great quip that I found was that in the 1960s, to get a particular image on a nice photographic plate, you would need to have a telescope of the size of a metre. If you wanted to take that same image today, you would only need a telescope that's 15 centimetres.
Wow. I mean, we've seen the same kind of leap across all kinds of photography. If you think about what your camera on your phone is capable of doing in 2018, wind back 10 years, that would seem like magic, utter magic. But it's all the same kinds of technologies, doing the best that you possibly can with the relatively small amount of light that's getting in through the front window, and then doing all sorts of very, very clever processing on that signal to figure out what you're looking at. And whether that's a camera phone, a smartphone, or whether it's looking through a telescope, it's the same kind of technology. And I'm guessing that we've probably actually nicked a lot of that technology from the astronomers and brought it over into other fields as well.
Yeah, especially the low light level kind of photography, because we're looking at, by nature of our work, very, very faint objects in the sky.
Yeah. So astrophotography. Now, we need to be a little bit upfront about this one. Look, we do know, please don't write into us with this particular thing. We do know that a podcast is an audio thing, right? You listen to it. But astronomy, as we've said on a number of occasions, astronomy is a very visual thing, and we like to put pictures up on with the podcast. So if you're listening to this through the right kind of player on the right kind of device, you might have noticed that pictures come up along the way with the podcast in the player. But you can also have a look at all of the pictures that we're going to be talking about in the show notes. We'll put links in the show notes. We also try to make a YouTube version of every episode, so you'll be able to see the pictures there. We are going to be talking about images today. And so if you want to follow along at home, then it's probably worth finding one of those ways to check out some of the amazing astrophotography images that we're going to be talking about as we go. Because, Emily, you've picked out some of your all-time faves.
Definitely, yeah. So we've got 4 images that we're really going to talk about in detail today.
Where are we going to start this one?
What's the most famous image in astrophotography, do you think? Probably exists, or at least where do you think that those images have come from?
Well, I mean, it's got to be Hubble,
Yeah.
right? I mean, Hubble is the amazing orbiting satellite telescope that just changed the way we look at the universe, or at least changed the way we perceive that. You know, it puts so many images out there into the public saying, look at this. This is staggering. And Hubble just kept chucking them out there and go, really? That's out there? Wow. And then it'd turn around and go, look, and this one. And then there's Saturn, and then there's this nebula. Like, Hubble is responsible for all of that.
Yeah, it's amazing.
So it's got to be a Hubble
Totally
one,
amazing.
right?
Of course it is. And I've said it before that Hubble was one of the major reasons why I decided to become an astronomer, because I saw those pictures coming out in the 1990s and I just wanted to know, what is that?
Going on? What are you even looking at, Hubble? So just a quick aside, we did talk about this a while ago, but I've forgotten. When did Hubble first go up? How long's it been up there?
So it's been up since 1990.
1990.
In fact, I had a quick look, and as of today, it's been in orbit 28 years, 7 months, and 6 days.
And it's still going.
It's still going.
I mean, that's staggering.
And I think it could go for another 10 years.
Absolutely staggering. And they did have a few problems along the way. They've had to have a couple of little services, getting in there, lifting up the bonnet and tinkering with the donk and that kind of thing. But it's still going.
Yeah.
Absolutely
fantastic.
amazing.
Yeah.
Absolutely. Wasn't there a thing recently where they needed to give it a bit of a tap or something? Was that Hubble?
One of its gyros, yeah.
That's right.
Yeah.
And didn't they do the fabulous, what if we turn it off and then turn it back on again? And didn't that basically work?
It basically worked.
I love that. Absolutely love it. You can imagine the meeting back at Hubble headquarters where they go, what are we going to do? How are we going to fix that? And someone puts up their hands. Have you just tried turning it off and turning it back on again? And it works. I think that's brilliant. Okay, so we're going to start with a Hubble image. Mm-hmm. Which one? Because there's so many.
There are lots, but I've chosen one that's really one of the ultimate classics.
Okay.
And it's definitely one that I remember seeing when it first came out. And that's it's the full image is part of the Eagle Nebula, mm-hmm. but it has the very, very famous and very, I think, evocative title of the Pillars of Creation.
Yeah, this is, if you've seen any Hubble pictures, you must have seen this one, the Pillars of Creation. It looks like fingers stretching up into the nebula. It's so 3D, it's so evocative, it's so there. And one of the things that I've always wondered about this picture, but I've never looked into, so maybe you can help me out here. What's the scale of it? And again, if for those following at home, go and check out this image, whether you can look at it on your device now or go to one of the links in the show notes. Go and check it out and have a look at it while we discuss it. What's the scale of this image? What are we looking at here?
So this is a huge cloud of gas and dust that's about 7,000 light years away from us.
Okay.
So pretty far away. And the scale in terms of the size of each of those fingers, they're kind of a few light years long. So they're pretty enormous structures. That's
really big.
Really, really big.
If you're thinking about in terms of the, how big is big, then what's the distance from us to the next star, the closest star to us?
Yeah, so that's just over 3 light years.
3 light years. So these fingers are a couple of times that. So you could fit our solar system and the next one over and the next one after that, in distance, inside one of these fingers. That's big. So what are we looking at? What are they?
So, yeah, as I say, this is cloud of gas and dust. And the reason why they're called the Pillars of Creation is because this particular cloud is collapsing under its own self-gravity at particular points. And you can see this particularly in the very tips of the fingers. And new stars are being born.
Cool. It's a little stellar nursery.
It's a stellar nursery, yeah.
Whereabouts? Where are we looking?
So in the sky.
Yeah. I knew it was in the sky, Emily. Come on. This is episode 25. I've got that far.
It's in a constellation somewhere.
Okay.
I can't remember exactly.
Right.
It's Lyra, I think.
I'll let you off on that one. I have been throwing questions at you. You've done well so far.
It's 7,000 light years away, Chris.
It is, yes. And up there in the sky. In the sky. Brilliant. So we've got these little stellar nurseries. Why are they finger-shaped.
So the wonderful thing is that when new stars are born, then they put out lots of new light. And particularly they put out lots of really nasty light, actually. We've mentioned before, stars being born is not a very pleasant process at all.
No, it's not nice.
And they put out particularly ultraviolet light. And this ultraviolet light, it starts to erode the rest of the cloud that these stars are embedded in. So particularly in the tips of these fingers, you can actually see the new stars kind of blowing away all the gas and the dust that they were formed out of, basically.
So the structure you can see is actually that gas and dust being just mixed and messed and blown around by all of this energy coming from these new stars being formed.
Yeah,
wow.
Yeah, it's really exciting. In fact, there's a complementary image to this. So Hubble looked at this in 1993. I think the image came out about 1995. And for the 25th anniversary of Hubble, of course, because it was such a famous picture.
So iconic, yeah.
Yeah, they went back in 2015 and did it again. And of course, Hubble hasn't changed a huge deal.
Yeah, the instruments are still the same.
But our image processing has gotten a huge amount better since then. And so the newer image from 2015 is just mind-blowing. And then to complement that again, they went back and looked at it in the infrared. And in the infrared, the image is just amazing, again, because it's very ghostly. The infrared light's actually able to penetrate into the clouds, and you can sort of see through the fingers and see the stars that are on the other sides of them.
Wow, yeah, because of course in astronomy you're not just looking in the visible, and we can get to more of this in a second, but you've got, all the different colors through the visible, but then you've got your infrared and your ultraviolet and right through to X-rays and gamma rays, radio waves down the other end of the spectrum. You've got all those different ways that you can look at things. And those different kinds of light, those different wavelengths or frequencies of light can get through different kinds of material. And so whereas one of them might get blocked, say visible or ultraviolet, maybe the UV can get through and show you some structure that you couldn't see in other ways. Can we talk for a second about Hubble's its instrument? Because if you look at one of these images, it looks a little bit like, wow, does it actually look like that? Like if I could see it with my eye, is that exactly what it would look like? Is that from one instrument, one camera, basically? Or is it a combination of a bunch of different images put together? What are we looking at?
Yeah, well, this is where astronomers have to own up a little bit to reality.
Come clean.
So we do tinker with our images quite a lot from space. And the reason for that is because we CCD cameras that we use to do astrophotography or even the science that we use are not color cameras. They're actually black and white.
Oh, okay. So the color is put in later?
Yeah, so what we do to generate the color is we take the image of the same field, but we put different colored filters in front of it. So although what the CCD detects is black and white, what is white, if you like, where there's lots of signal, is going to be where there's lots of light from that particular color.
Right, so it's not, it's black and white in the sense that it's only, the pixels on the camera are turning on or off. Right, it's not seeing in several different colors at once, but you are focusing in on. Well, let's have a look at this particular band of wavelengths. So we're looking in red now, and if you know that picture has been taken in the red part of the spectrum, then let's call that red.
And there's lots of different coloured filters you can use, some of which include a lot of colour all at once, and so you get a lot of light through, and some of which are really, really specific, and you can only see a very, very specific colour. You do get something called true colour, which is where we try and mimic exactly what the eye would see. And you need 3 filters for that, red, green and blue. But often the things, and you can get 16 million colours if you combine those two. So you can build every other colour in the spectrum.
Which is basically what your television's doing, right?
Yeah.
Or your phone or any other screen is putting together little dots of individual colours, red, green and blue, and making all of the colours that we see on our screens. That's all they're doing. This is just reverse engineering that from the Hubble pictures.
Yeah, and you do see some true colour images, but sometimes to get the most out of a particular astrophysical object, you need to take filters that are a bit different to what the human eye might see and combine them with colours that are a little bit different than what we would see.
And I guess that kind of makes sense as well, because why limit ourselves to the stuff that our eyes would be able to detect? We're very human-centric in the world, because that's who we are. But of course, we can only perceive one tiny little bit of the entire electromagnetic spectrum, leaving out any other kinds of astronomy, neutrino astronomy and gravitational waves. Forget all of that. Just looking at the electromagnetic spectrum, light, we can only see a tiny little bit of that. Why would we limit ourselves to that? And some of the most amazing pictures are surely putting together all sorts of wavelengths that we wouldn't ordinarily be able to see. That's kind of the point.
Yeah, certainly. So that infrared picture, for example, of the Eagle Nebula, that is something we just can't see with our own eyes, which is pretty cool. But this particular Hubble picture, so what they've done is they've put 3 different coloured filters together. So they've used filters that are looking at particular chemical elements that we know exist in these types of systems. So in this case, we've got oxygen, we've got hydrogen, and we've got sulfur.
Now, when you say that, so are you saying that they're looking at wavelengths that those chemical elements would be emitting when they're excited, right? Different atoms, different molecules, when they get a bit of energy in them, they'll get all excited as atoms and molecules, and then they'll release that energy again in very specific ways, in lines that we see in the electromagnetic spectrum. So it'll be at a very particular wavelength or a very particular frequency. So that's what you're saying, is that we're tuning into, well, let's have a look and see what is coming out in that oxygen wavelength and what's coming out in the hydrogen wavelength. Is that what you mean?
That's exactly right, yeah. So, for example, oxygen is at 502 nanometers. That's kind of near the middle of what we can see in terms of colours. And so it might be a little bit bluey-green to us.
Right.
But in the Hubble picture that we've got here, that's chosen to be coloured as blue.
So when you see, just to clarify that, when you see astronomical photographs and they talk about, this has been taken in the oxygen or in the hydrogen, that's what they're referring to, is they're focusing on that particular wavelength.
Very specific. So, gotcha. So in this case, we've got oxygen as blue, the sulfur is red, and the green colour that you see comes from, it's a mixture of nitrogen and hydrogen. All these really important chemical elements that we can see. And that tells us, you can see the kind of the physics going on there too.
Yeah, I mean, that does a lot more than just say, hey, doesn't this look pretty? It's telling you where these materials are, where these elements are. So what does that tell you about what's actually going on in the picture?
So you can see there's a lot of red in these pictures, and that's because there's so much hydrogen in the universe. And we see huge amounts of, it's sort of, you can see a bit the distribution of that in terms of where you see the pillars themselves. A lot of the darkness that you see is actually dust and very cool molecular clouds. So these are really, really dark, dense clouds.
I mean, they almost look like voids. They look like they're empty, but they're not. That's actually clouds of dust and cold stuff.
That's all the cold stuff. And then you can see the glowing around the tips, which is where the new stars are being born.
Wow, very cool. Such a good picture. Moving on to the second of your 4 chosen astrophotography images today. Where are we going after that one?
So, second Hubble picture, and this is a slightly more recent one. This came out about 2 years ago. This is a picture of the Andromeda Galaxy.
Yeah, I know this one. This is one of my favorites. And Emily, you know this is one of my favorites.
I know this is your favorite.
I freak out about this one because it just gets me every time. Okay, so what are we looking at?
Well, I kind of lied when I said it was a picture.
Mm-hmm.
It's not just one picture.
No, it's not. I remember.
It is 7,398 exposures taken pointing the telescope 411 different places.
Blimey. I mean, this is the equivalent of what you used to do when you would, you'd go somewhere really interesting. Like I used to do this down at Sydney Harbour when I lived in Sydney, and it's such an amazing view. And you've got the Opera House over here and Sydney Harbour Bridge over there and the bay over here. And so you would just take a picture that way and a picture that way and a picture that way, and then you'd string them all together into one long panorama. And so I've just made one big picture out of half a dozen photos, and it never worked the way I thought it was going to. But this is a similar kind of idea. Let's take a big picture of the Andromeda Galaxy from how many?
7,398.
See, I mean, that's going a very long way to get a good picture. But it's worth it because this one's an absolute cracker.
So this is the largest Hubble Space Telescope image that we have created. And it's what I like about this is that, you know how you get in kind of the crime show sort of style films or TV shows when they're able to use these video cameras of a particular suspect, or they're looking at a number plate, and they seem to have this kind of infinite zoom.
Enhance and go in, and you sort of go from this incredibly pixelated thing to, I can read the writing on that person's notebook, and it's you
could just
That's
zoom
not
in
possible.
and zoom in and zoom in and zoom in. And this is an image where you can actually
do that. I mean, this one's not mucking around. You can you see it when it fills up your computer screen or your phone screen, and you can see a lot. There's a lot of stars in this, And I mean, that to me is one of the most amazing things straight off the bat is the images that we normally see of other galaxies. They just kind of look like a wash, right? Any stars that you see in most of the pictures of other galaxies are actually stars in our galaxy that you're looking past. And you can see some of those in this image. They're the big spangly things that are kind of in the foreground. But you look at this picture of Andromeda and you can just see this wash of dots. You're looking at stars in that galaxy, billions of them.
And then you can zoom in.
And then you can zoom in and see even more stars.
And then you can zoom in again.
And then you can zoom in again.
And every time you think, this must be it. This is it. I mean, this is a galaxy. This is not our own galaxy.
Yeah.
This is a galaxy that is 2 million light years away from us.
Totally whole other galaxy. And there's, every time you zoom in, there's always one little spangly star in the corner. And no, that's in our galaxy. That's in the Milky Way. All of this other stuff is in another galaxy. And that's off the charts of amazing. But the one, and that I get off on this one, the one that I really love is that in some places you can zoom into the point where you can see gaps in between the stars. You can kind of look through. So we're looking through our galaxy, through Andromeda, and you can see stuff in the background. You can see other galaxies in the background of the Andromeda galaxy, between the stars in Andromeda galaxy that we're looking at in between the stars of our galaxy. And if that doesn't mess with your head, then you're not switched on right. I'm making that statement right here, right now. Need a little break.
Yeah.
No, I'm all right. I'm okay.
It's okay, Chris. It's okay.
I know. I get riled up about this one, but it is.
And it is beautiful. And it's most of one side of the Andromeda galaxy. So you sort of see the core, and then you see some of the spiral arms out to the edges. And even in this picture, I think there's about a third of all stars in the Andromeda galaxy, on the order of 100 million stars.
It's absolutely staggering. And Andromeda's quite similar, we think, to the Milky Way. Isn't it?
Yeah, another big grand spiral.
Yeah. I mean, Andromeda's a little bit bigger, I think.
Bigger.
But otherwise, structurally, looking at Andromeda is a little bit like what we would see from Andromeda looking back at ourselves.
Yeah, and you can see that. You can see the spiral arms.
Yeah.
You can see these dust lanes moving through, and the spiral arms. It's just gorgeous.
Yeah. And I think that's partly why I get so riled up by this particular image. Is for me, it's one of those images that really is. That it changes your view of the universe. You're looking at something which is on a scale, on a level of detail, just so awe-inspiring. And the fact that it is a little bit like, what it would be like looking back at ourselves. That it's hard to get across in words how small that makes us feel here on Earth and how vast this thing that we're looking at in the sky really is. Ah, dear.
Fabulous.
Andromeda. Gotta love it.
Gotta love it.
All right, where do we move on from here?
So actually I wanted to then move slightly away from Hubble and talk about one of my favourite professional astrophotographers and great fan of the show.
Yeah, friend of the show.
Friend of the show is Chris Baker. And what he does is he takes photographs from a telescope that he runs remotely in Spain.
Yeah, it's on the top of a mountain in Spain, isn't it?
Yeah, it's so cool. So first of all, remote astronomy is just... awesome.
Well done.
Yeah. You can sit there watching a Netflix nicely curled up at home in the UK and then turn on your telescope and start your observing, which is very cool.
Yeah, I think I want that job, actually. That's pretty good.
And it's a fairly modest-sized telescope, actually, but the images that Chris is able to create are just mind-blowing.
Now, when you say modest-sized telescope, what to an astronomer or an astrophotographer would be a modest-sized telescope?
Okay, so to give you an idea of scale, the
Yep.
biggest research telescopes in the world are on the order of 10 metres.
That's
in
diameter. Right,
Yeah.
it's 10 metres. That's quite big.
It's pretty big,
That's a big mirror to shape and polish.
Yeah,
Well
definitely. The research telescope I use is about 1 metre
Mm-hmm.
in size, and Hubble is 2.4 metres in space.
yep.
So, big,
So
big
bit
telescope.
bigger than I am tall. Yeah.
Chris's telescope is 6 inches.
6 inches. Okay, modest.
Modest.
Yeah.
But beautifully designed telescope, I have to say. It's not just something you fell off the back of the truck. It is a gorgeous, gorgeous telescope.
And he does take some amazing images. We've got actually some here in the physics department at the University of York, haven't we? Because he prints these on glass, right? And this isn't just an ad for Chris's work. we do rather like Chris's work, though. So why not do an ad for Chris's
Well,
work?
definitely,
Definitely
yeah.
have a look at the link in the show notes for those. But we've got one, and it's actually a nice link from the previous image you chose. We've got a picture of Andromeda out there in the
Yes,
hallway,
yeah,
haven't we?
yeah.
Which you can buy for Christmas. I don't know. I won't give you the full plug, but he does sell them, and they are amazing.
Yeah.
It's beautiful.
So what Chris has done is he's a fantastic astrophotographer, but he also knows what he's talking about when it comes to printing things. So he's printing his images onto glass, which makes them just look astounding.
They just glow. Yeah,
it's much better than kind of the printouts that I used to do on my computer and stick them on my wall, right?
So he's got a 6-inch telescope on the top of a mountain in Spain. Now, the top of the mountain part's important because you're getting a long way away from the city and the lights of the city, and you're up where the atmosphere is a bit thinner. Does that
A little
make a
bit,
difference?
yep. That makes a big difference, actually. The weather tends to be a bit more stable. Light pollution's pretty much zero. So it is a fantastic site. It's one of the few places I've actually seen the Milky Way in the Northern Hemisphere from. So it is gorgeous.
Very nice. Okay, so this is Chris.
Yes.
Which image are you choosing?
Well, I've chosen two, actually.
Two?
I
Okay.
couldn't possibly decide. So the first one is actually from Chris's original collection that he did of images, and it's called The Witch's Broom.
Now, you were showing me this one earlier, and I wasn't familiar with it. The Witch's Broom is part of
The Veil Nebula.
the Veil Nebula, which I was familiar with, but I don't remember seeing this particular image. So talk us through it. It's absolutely stunning.
Well, the Veil Nebula is quite a big structure, actually. In fact, it's something like 6 times the size of the full moon across the sky.
Wow.
If you could see it.
Yeah.
Which we can't.
Which we can't.
because we don't have 6-inch telescope for eyes, which
Yeah.
is a shame, really.
But, I mean, it's the sort of thing which, again, it must have been amazing the first time that people started seeing these structures and going, hang on, this is huge in the sky. We didn't even know it was there. Andromeda being a classic example. It is. It's massive in the sky. It's like 6 or 8 moons across, or something, in that order. And this is similar. These are huge structures, but they're just so dim we can't see them unless you start getting a nice big telescope and pointing at it.
Exactly, yeah. So the light's really diffuse, and you need to kind of have an exposure where you open up your shutter and just wait for minutes, if not hours, for that amount of light to come through into your telescope, onto your CCD, so that you can actually detect it, which is not something we can do. I mean, I can't open my eyes for several hours.
No, I mean, your eyes do get used to the dark, and when you do go out on a really clear night, if you look up at the sky and go, wow, there's a lot of stars. And then if you wait a couple of minutes, no, there's a lot of stars. Your eyes have gotten used to it and you can see a heck of a lot more. But it plateaus after a little while.
Yeah.
You're not going to see this nebula.
No.
Fortunately, Chris can. So
Definitely,
what
yeah.
are we looking at?
So this is different again, actually. So a lot of nebulae are to do with things like stars being born. So, for example, the Eagle Nebula. But this one is actually the opposite.
Right.
This is a star's death.
Oh, okay. Is this a supernova remnant?
This is a remnant of a supernova.
Cool.
So
right.
cool. So we think that a star that might have been about 20 times bigger than our sun kind of ran out of fuel and exploded in the biggest explosions that stars can do about 8,000 years ago.
Right. And these explosions are very big.
Yeah.
Yeah. They outshine entire galaxies.
That's
so
huge.
these are big explosions. And so one might imagine that after the explosion, they leave something of a wake behind. There's a bit of destruction in their wake.
They're pouring out energy into these huge bubbles of material and just energy that's moving through space. Now, it turns out that the space between stars is not actually empty.
Yeah, I mean, space is actually, it's a bit of a misnomer, isn't it? Because it's not space, it's stuff.
It's just not very much stuff.
Yeah, but enough that if you put a huge amount of energy through it, like after a supernova, then it does something.
Yeah, so this is the shock wave of that supernova still traveling through interstellar space.
Cool.
And it lights up. And again, these chemical elements that we mentioned before. So this one's got oxygen, sulfur, and hydrogen again.
Oh, right. So as the energy's passing through, it's encountering stuff along the way, exciting that, and then that's emitting light. And that's what you see in these nebulae.
Yeah.
Right.
Just gorgeous. It's just a big shock wave from this enormous explosion. This particular object is quite far away, but it is the closest one that we're kind of mentioning today.
Right.
So it's only 1,500 light years away from us.
Only 1,500. But that's still within the Milky Way. We're still situated within the Milky Way with that one.
Yeah. So it's just a gorgeous example and kind of the nice parity, I guess, almost between you get these beautiful structures when stars are born and then when some of them die again as well.
Yeah, and presumably there's a bit of a cycle there that if you start chucking out enormous amounts of energy, I mean, I think we've talked about this briefly before, that when you chuck out an enormous amount of energy from a supernova, that energy can go on to kick off processes in other places that start the whole cycle over again. That you can get stars starting to be formed in other areas as a result of the shockwave from a supernova.
Yeah, and there's two parts to that. There's actually the material that comes out of the star. So stars take lighter elements and make them into heavier ones. They push them back out into this interstellar space.
Right.
Then they get used up into the next generation of stars. So it's a big recycling kind of factory.
I think we need to talk about that at some stage in the future. I think that's a whole other podcast. But I remember hearing about the sort of thing you're talking about, and something to do with the fact that a lot of the heavy elements here on Earth have been through a couple of cycles of stars by this point and until they got to us, which I think is off the charts fascinating. So let's park that one for episode down the track. But yeah, fascinating stuff. So in this particular picture, we're looking at one part of that nebula, which is called the Witch's Broom,
yeah.
which is really nice and
so it's
evocative.
just a beautiful structure, and you can see the nice color difference between the different filters, and it's one of those evocative images. You think, oh, that's interesting.
Now, is he combining different images to make this?
Definitely, yeah. Right. So first of all, it takes hundreds of hours to make any of these images, right? You've got to take exposure after exposure after exposure of the same thing, exactly the same filters, and you use that to really stack up your signal so that you get enough light coming into the telescope, basically.
Now, there's a lot of automation and machinery going on here, because if it takes that amount of time to make one of these images, the Earth turns, Emily. I don't know if you know this, but you can't just point a camera at the sky and expect the stuff that you're looking at not to move out of your field of view. So he must have some pretty sophisticated equipment to be able to keep tracking the thing that he's taking pictures of. Otherwise, it's all going to be really blurry. Yeah,
so modern telescopes are very finely tuned so that they know exactly where they are and therefore how fast the sky is moving above you, or really how fast the Earth is rotating, so that they actually follow the same piece of sky over a course of a night or several nights.
Which it doesn't surprise me in the slightest that the big research telescopes are able to do that to, pinpoint accuracy. But I find it fascinating that you can... That someone who is, yes, he's definitely professional astrophotographer, but working with a modest-sized telescope, as you described it, is able to take images with this level of detail, which obviously requires enormous accuracy in where you're pointing this thing over long periods of time. That's some sweet technology.
And a lot of patience.
Yeah.
A lot of patience waiting for those clear nights and getting those images down. Cool. So
excellent. So that's photograph number one of Chris's. Yes. So we've got one more to go. What's our last picture for the night?
Well, this has got to be one of my all-time favourite objects in the universe as a whole. And the fact that Chris has done this outstanding photo of it just makes me fall in love with it all over again.
All right. What are we looking at?
Well, romantically, it's called the Rosette Nebula.
No.
I know.
They're nice.
Cute, huh?
Yeah.
And I really, really love this particular patch of sky just because it's pretty, right? It really has a lot of really interesting structure in it.
Yeah, undeniably. I mean, this is one of those images that's like, that's a poster on the wall.
Definitely,
it's got to be. It's a classic... astrophotography iconic image.
Yeah, it's a work of art in space just on its own.
Yeah.
Right. And then what I super, super love about it is that it's actually a beautiful example of a piece of physics as well.
And, you and I both would agree that if you can combine art and physics together, that's the best of both worlds.
Of course.
It's got to be that way. So what are we looking at?
So this is another star-forming region. So we've got huge amounts of gas and dust, mostly hydrogen, but, sprinkle a bit of other stuff into there as well. We've got something like 2,500 young stars in this sort of region of space. So, when we say that stars are born in nurseries together, we're not really kidding.
Yeah, it's not like a couple. It's not twins or triplets. You're talking several thousand here. Wow.
Yeah. And so what's happening is you've got this big cloud. It's mostly neutral hydrogen. So that means it's hydrogen it's got its electron still with it.
So it's not really energetic to the point where it's ejected its electron, because that tends to be what happens. If hydrogen or any other element, if you put too much energy in, then the electrons start pinging off and you've got ions at that point. You've got charged clouds of gas. But this is energetic enough to be giving off light, but not so energetic that it's been stripped of its electrons.
That's right. Well, the gas and the surrounding the rosette, if you like,
Yeah.
the stuff that you can see, that's definitely neutral hydrogen. And what happens is when you excite hydrogen, it has a way of kind of releasing that energy in terms of the different colours of light it puts out. It absolutely loves to put out light at red wavelengths, which is 656 nanometers.
And is that what we're seeing in this image? Has it been coloured red? Because
So it's
again,
not-
remember, it's all black and white.
Yeah. Traditional images that you see of the Rosette Nebula do have a lot of red in them. Now, Chris has chosen a slightly greenish colour because it's kind of somewhere between red and green, this hydrogen, which I think
So a bit of
makes-
artistic license there.
Well, yeah, and it makes it really pop, actually. You can see the difference in colours. So it's really, really cool. You can see that hydrogen. But then you have this kind of hole in the middle, right, of the nebula. Well, it turns out there's still stuff in that hole.
Oh, because I mean, it does. It looks quite empty. It looks blank.
You can see through it into the next, bits of stars, and you can see background.
So what's in there?
So that is actually still hydrogen, but this is where you actually do have enough energy to ionize your hydrogen.
Okay.
So the electrons are now dissociated from the hydrogen atoms, which makes the hydrogen gas transparent. So you can see
There's some
through
interesting,
it.
yes, there's some physics in there that we can explore, but we won't. But the bottom line is, at least at these wavelengths, it's transparent.
Yeah.
Okay.
So you get this kind of hole that you can see into. And this particular hole, it's in 3 dimensions. It's a kind of sphere. It's this bubble, and it's called a Stromgen sphere.
Stromgen sphere.
Yeah.
Named after Stromgen, Professor Strom.
Yeah, definitely.
Professor Stromgen.
Yeah.
Yep.
So the Stromgen sphere, and the reason why the Stromgen sphere exists is because those brand new stars that have been born are pumping out huge amounts of ultraviolet light. And you need to get to the ultraviolet in order to have enough energy to strip away these electrons and ionize your hydrogen.
Right.
So the fact that you've got these brand new baby stars being born, they're outputting all this nasty ultraviolet light, actually kind of clears the sphere, if you like, of the Stromgen sphere.
And so gives us this amazing rosette structure where you've got all this beautiful neutral hydrogen around the edge, and then this lovely sphere in the middle.
Yeah.
It's dark.
It's fantastic.
Yeah, really nice, really nice. And again, where is this?
So this,
I'm going to throw that one at you. It's in the sky.
it's in the sky.
That's
you always
okay.
ask me the hard question.
I do.
I'll tell you how big it is.
Okay, how big is it?
So it's 130 light years across. So quite a lot bigger
Yeah,
than
that's big.
the fingers, for example, that we're talking about. But the Eagle Nebula itself is much, much bigger than the Pillars of Creation.
Yeah, pillars. That's just one bit of it, isn't
Yeah.
it? It's a much bigger structure. But this one's 130 light years across.
Yeah.
That's quite large.
Yeah, and it's got a whole total mass. If you were to weigh all of this and work out the mass of this cloud, it would be something like 10,000 times the mass of our sun.
That's quite a lot.
Very, very cool.
It's quite a lot. But then, if you've got several thousand, couple of thousand, did you say 2,500 stars being formed? Yeah, you'd need a lot of mass to do that in the first place anyway. Otherwise, you're not going to get stars.
And there's more to come. These stars are just constantly being formed in this region.
Wow. Gorgeous. Gorgeous. Okay, so that's the top 4 images.
Yep.
At least for today, anyway. There's so many that we could have chosen. But in order to close this one off, here's a question for you. If someone out there in listener land wanted to get some kind of toehold on astrophotography, like how do you start? Is there something that you could do to just go and get your first photograph?
Yeah.
First astrophotograph?
Luckily enough, you don't have to go out and use the Hubble Space Telescope as a first
Few.
go.
Neither do you have to have your own patch of land on top of a mountain in Spain.
No. In fact, all you need to have is a camera that's capable of taking a long exposure. And this is really important because I know that I tried when I was younger, just getting out my old digital camera. I was like, oh, the Milky Way is up. That's really pretty. Let's just take a picture. Darkness.
Yeah, it's a bit harder than that. It's a bit harder than
Turns
that.
out your eyes are more sensitive to the kind of light that's coming, and you need to have longer exposures to get enough time to get all the light into your camera.
Yeah.
So really you're looking for any type of camera that you're able to hold open the shutter for around about 30 seconds.
Yeah. Now there are apps that you can get for your smartphone that will allow you to do that as well. I haven't tried it out though. I'm not sure how good the sensor, the image sensor in your average smartphone is going to be if you hold the shutter open for that amount of time. But it could be worth a try. But otherwise, we're
okay.
talking about digital SLR cameras and so on, where you've got that kind of control.
Yeah. And what you really need to be doing when you have a 30-second exposure is to have some way of keeping your camera incredibly still.
Yeah, you can't handhold this one. That's not going to work. You need a decent tripod to
Yeah.
keep it still. And not just that, but ideally a way to press the shutter button remotely.
Yeah.
Either after a period of time, so that, you can put it on a setting where after 5 seconds it'll open after you push the button, just so that the vibrations aren't there, because any vibrations you've got are going to come through and shake your picture around.
Yeah. And so this is the perfect kind of setting if you just want to take some pictures of what the night sky is looking like. You'll see stars, you can see the Milky Way. If you want to take pictures of the moon, you might need to trim it down a bit. The moon's quite bright.
Yeah, that's always the one that gets me, when you see a big bright full moon, you see people out there taking pictures of it with their phone, and you think that's just going to be so small. It's one of those amazing tricks of the night sky, that the moon can look so big, but if you take a picture of it, it's tiny. So you've either had to crop that or get a decent zoom. Yeah.
So if you want to take just general night sky pictures, though, wide angles are a good way to start.
Because you get a lot of stars in.
Yeah.
Get a lot of stars.
Get the Milky Way. It's
For
really
a sort of 30-second, 1-minute exposure, things aren't going to move that much, are
30
they?
seconds, I reckon you can get away with. Probably more than that, then you start to have, again, the Earth is moving, it's rotating, so the stars appear to move in the sky, and therefore you start getting star trails.
Yeah.
So
Yeah, which is something, if you want to go for that effect, you can get some amazing effects with really long exposures over hours, minutes and hours. You can get these really long star trails across the sky.
Yeah, and star trails are gorgeous in their own right. So for doing star trails, you want to be looking at taking things that are 20, 30 minutes and maybe even stacking them up. But this is where you can really, it's quite cool when you think about what you're seeing, and you're seeing the physics of the Earth spinning, which makes all the stars above you rotate around a central point.
Yeah. In the northern hemisphere here, around the North Star, which is kind of cool. In the southern hemisphere, there isn't a star at the pole. You've got the Southern Cross, which points to it, but you kind of got this void where that would be.
We don't have a South Star.
We don't. No.
One day we will, but we won't go into that. Yeah, and the other thing one to try is, of course, meteor showers.
Ah, yes.
If you get set up and get confident doing some snaps of the sky, look up when the next meteor shower is going to be and just take pictures and see if you can get lucky enough to capture a meteor going through your
Where would one go to find out when the next meteor shower is? One could Google, I suppose.
Yeah.
Go to a search engine of choice. Other search engines are available.
So Space Weather's a pretty good one. Heavens Above. There's lots of things. There's even apps you can get on your phone where it will alert you when there's going to be the next meteor shower. So these things are well predicted. We know kind of when they're going to be and where they're going to be in the sky.
And this is where the Earth, in its orbit around the sun, is coming into what?
It's sort of like a debris cloud.
Right.
And part of that debris is going into the atmosphere, burning up in the atmosphere. So we get these nice little flashes of light.
So particular times of year, particular times in our orbit, we know in advance there's going to be a whole bunch of meteorites, shooting stars across the sky in a particular part of the sky as well, because you often know where they're going to be coming from. And these things can be, how regularly would they be at their peak?
You can get to 60 to 100 per hour, which is pretty cool, yeah. I think the next one coming up for us in the Northern Hemisphere is the Leonids in December. But there's heaps of them throughout the year, and depends where you are, obviously, that you want to look up. If they happen during the daytime for you, that's not a good thing.
Yeah, that's not really going to help. But at nighttime's a nice long exposure, and you might get some really good trails there. Cool, very nice. All right, Emily, so right back at the beginning of all of this, I said something foolish like, there's a lot of people out there who might think that astrophotography is astronomy. And it's clearly not. There's a lot of astronomy which is not just looking at pictures of the sky and going, ooh, that's pretty. But at the same time, there is something intrinsically linked in here, isn't there? That astrophotography is actually really important.
It's very, very important. I mean, as I said, beginning, I got kind of into astronomy based on pictures from Hubble.
So from an inspirational point of view, it's clearly really, really important.
Definitely. And I think people in general really enjoy having imagery that they can look at. I mean, you can't go to look at a news article about a discovery to do with black holes or gravitational waves without seeing some kind of artist's impression of what these things kind of are, right?
Yeah.
We don't have any photos of those things. We can't take photos of those things. But we still have a visual thing to look at when we look at those articles to really trigger us and to get us thinking about what's going on in these scenarios.
So it's really important from that point of view, is to be able to give us that, I don't know, partly a mental image of the amazing variety of stuff that is up there, but also the inspiration that comes from seeing such a wide variety of beauty and staggering structure in the night sky.
Yeah, and it's not just for those who can see as well. There are people who work on, for example, taking images of galaxies and making those into tactile images so that we can really share that love of the visual representation with people who may not be able to see as well.
Oh, that's a gorgeous idea. I love that. That brings us to the end of this particular edition of Syzygy. Emily, thanks for bringing your top 4 images in. I think it's been really fun.
Yeah, it'd be really great if some of our listeners could tell us what some of their favourite images
Yeah,
are.
write in and tell us. Throw us some that we might not have seen before, or just why they're special to you. You know, Emily shared what images really got her involved in astronomy. I went a little bit berserk about the whole Andromeda thing. Send us what you think is really, really awesome. How can they do that? Emily, how can people get in touch with us?
Well, if you're on the Tweetyverse,
On the Tweetyverse, in the Twitterverse, yes.
Twitterverse, then you can tweet us at SyzygyPod. That's SYZYGY pod.
Mm-hmm.
We're also on the Facebook.
On the Facebook, yep. You can just go and find us at facebook.com/SyzygyPod, or just whack it into the search bar, the Syzygy Podcast. We do put these podcasts up on YouTube as well. I'm a little bit behind in the editing of that. Takes a little bit of time, but we will get there. And the lovely thing about that is that episodes like this one, which have a few images associated with them, you can watch the images as you follow along with the audio. So that's kind of fun too. Or you can just go to our fabulous website, Emily.
Yes, and that is syzygy.fm.
That's right. You can go there, see all of our past episodes, read all the show notes, and send us a comment if you want to go over to the form there and just send us a little email saying, hi, this is my favourite image and this is why. We would love to see that. If you really enjoy the show and you want to help us out, there's a couple of ways you can do that. First way is to share it. Go and tell everyone you know. Think of the people that you reckon would be really into this sort of thing and go and tell them, listen to the Syzygy podcast and point them our way, syzygy.fm. That's the number one way. But if you want to go even further than that, a really good way is to help us rise up through the charts in the podcasts by giving us a review. You know, you can go to Apple Podcasts or Google Podcasts or Spotify or wherever you listen to your podcast and give us a little review. Write some words, put some stars up, and that'll help other people to find us. So that's really important. The last way that you can help us, in order to do this show as well as we want to do it, to spend the time on quality editing that we would really like to do, and to dream up new ways of doing exciting astronomy podcasts, you can help us out by becoming a patron. Go over to patreon.com/SyzygyPod and you can become a patron of the show. You can pledge a bit of money, $1, $3, $5, £5, £10 a month, and help us to do what we do. Like our newest patron, who is Sho Fuji, joined us this week as a patron of the show. So huge thanks to Sho Fuji and our other patrons. It really is just stunning that people actually do that. I think that's fabulous. But that does bring us to the end of this show. As ever, we produce this here in the plush surroundings of Emily's office here at the University of York, where Emily is astronomer-in-chief. I think that's your official title. My name's Chris Stewart, and we will catch you next time for the very next edition of the Syzygy Podcast.
See you later.
Bye-bye. So, title.
You don't want to picture this guy?
Oh, that's right. Picture this guy. Because that's what was that? What's that famous misreading of the song lyric? Excuse me while I kiss this guy. It's the Jimi Hendrix song.
Yes.
Excuse me while I kiss this guy. Okay, Jimmy, whatever you want to do, that works.